How about now?
That's fine.
That's good. Okay.
Works. Thank you.
So thank you so much for inviting me. And it's actually really great timing to go back to back with Dorsa. I too want to talk about how to make these human models in a way that, yes, is intent-driven, but also maintains a lot of flexibility from data-driven methods, and at the same time maintain safety. So I figured I'd give you one example of our own approach to this, and also how it fits into the kind of the broader sort of research agenda that we've been following in my lab. But first, I just wanted to sort of also say a little bit about why we're using intent-driven models, kind of where this came from, and why we like them so much. So just to sort of set out a bit of notation, we're going to have a robot in some state XR, a human in a state SH. The robot has a goal GR. And in order for the robot to safely reach its goal, in the presence of a human it's also acting, it has to also reason about the person, right? So that's what Dorsa was saying. And in particular, you need to know sort of where the person will be in the future so that you can solve your own planning problem, which, you know, might look as simple as minimize some cost function for the robot, but make sure that you're not going into states that the person will be in at the same time. And so to do that, so in order to do that, right, this gives you a way to sort of look at all the possible trajectories that the robot might take and decide which one it actually meshes well with what you think the person will end up doing. And so you need this predictive model. You need to figure out these states that the person will be in. Now, what are the states the person will be in? Well, the states that the person will be in will be based on sort of the decisions, the actions that the person takes, right? So what previous state they were in, what actions they decide to take, and then roll that forward. And so predicting the states that the person will be in is really a matter of predicting the actions that the person will end up taking. What are these actions what are the decisions that the person ends up making? And that's a dog barking outside. Sorry, it's really warm in San Francisco, so I have my window open. So what are these decisions? Well, there's a control theoretic approach, which will say we have no idea what people do. It's really hard to model people. And so we're gonna think of the set of all possible actions that the person could take and assume that anything goes with equal probability, and we have to safeguard against all of that. So that leads to this notion of a forward reachable set, where you look at these sets that just kind of evolve over time to be anywhere that the person might end up being. And now the robot's job is to make sure it doesn't intersect with those sets at that particular time. And this leads to really safe robots. It also leads to really useless robots. So here we have Alice walking in a room. On the right-hand side, you see the four reachable set corresponding to Alice. And we have a robot on the other side of the room that just needs to reach its own goal, but make sure that it doesn't run into Alice. And so they start going. Hopefully this video will play. And the robot is trying so hard to protect against this worst case adversarial version of Alice that Alice might just turn away and run straight towards the robot and chase the robot and hit it. And the robot's trying very hard to protect against that. So Alice, without just even trying, ends up driving the robot to the edge of the room. So I don't like the control theoretic perspective, at least this vanilla one, because it is safe, but it's kind of useless when you have close proximity interactions. Same happens when you have autonomous cars, right? If I have to protect against the worst case, then I get really screwed because you have people coming the other way in the other lane, basically 1 meter away, and those might just run into you, and so you have to teleport yourself out of the scene. So, okay, we can't rely on four reachable sets. There's an alternative approach, is just to rely on data. So this idea is that offline, we can collect a lot of data of people moving around in rooms and in driving and so on. And we could train a policy that imitates their behavior, right? And we're not using that for the robot, but we're using that as our model of how the person is acting, a mapping from states to probability distribution over actions that the person might take. So this is all well and good. The challenge with this, though, is that what ends up happening is, let's say here's the space of all possible policies, all arbitrary policies you could define, all mappings from states to probability distribution over actions. Imagine that set right there that I drew is that space. Very few of these are policies that a real human would ever take, right? We don't act completely arbitrarily. We act in sort of somewhat structured ways when we move about. And so there's some very small subset there of all arbitrary policies that corresponds to real human policies. And the challenge is you can collect a lot of data. And what will still be the case is that there will be many different policies in your full space of policies that are consistent with the data that you collected, right? So some of them will be in the space of actual human policies, other ones would be outside of that space. And this is a problem because now we're saying, well, we kind of need to get lucky so that the policy we happen to pick that's consistent with the data we get is in that very small space and not, completely arbitrary outside of that. And we see this happening and getting that disambiguation wrong and that causing problems. And I don't have a great example for sort of moving around people, but I have a really interesting example from a different domain that we work in. This is kind of a silly collaboration domain. This is a benchmark task for collaboration that we made that's inspired by this game called Overcooked that I play a lot. And what happens in this simple task, it's actually a really hard planning problem because it's task and motion planning, hierarchical, everything. But basically what happens here is you have, let's say, a robot, an agent, and a human. So this avatar is driven by the human, and they need to collaborate on preparing essentially these meals. So these are onions over here. These are soup pots where you can put the onion and it turns into soup in some time. And these over there are delivery areas. And so here's a policy that is trained via imitation. So we train a policy, we collect some human data, train a policy via imitation. We ran it, so now both agents are running that policy just to see what the imitation behavior looks like. And they end up, in this case, collaborating really beautifully. So what you see is that the right-hand side was prepared with a plate to take the soup that was cooking. The left-hand side was having an onion, prepared to put the onion in at the time that the other guy took the onion out, took the soup out. And so it just kind of beautifully works. And so this is encouraging, yay, data-driven. And then we did something a little different. We put one plate on the counter over here, and this just breaks everything. So you would think that this guy over here had some soup. You'd think that he went to deliver it, but no, he just went to put it on the counter, because why not? This one is also running around aimlessly, also not delivering things, trying to grab onions, but he also has soup. So they're not even trying to make soup anymore, and they're not even trying to deliver the soup anymore. It's just complete chaos, right? And so it's kind of deceptive because you look at in-distribution data and you say, oh, they've learned so much about the task. And then you look at out-of-distribution data, we change one small thing and everything breaks. And so this is my frustration and disappointment with trying to learn everything from data. And just kind of as food for thought, or something that I thought was really interesting. Here's a plot. This is all in simulation, but here's I want you to focus on these gray lines over here. So what they are, this is robot cumulative reward in a setting where you're trying to learn a model, a black box model of the human, and then use it, have the robot use it, do reinforcement learning to respond to that and do well in the task. And you can see that these are really flat, both when you're using off-policy data, so you collected a bunch of data of maybe human-human interaction and you're trying to use it, and it's flat when you're using on-policy data as well, meaning you collect a bit of data, you train with it, and then you roll out your best response, your policy, and then you collect more data. And so this sort of adaptive procedure, sort of dagger style that tends to work, can completely break in certain interactions. Because you never get exposed to the data that you really need to see of the proper interaction with the human actually happening. And so you can fix this over time with some really idealized magical exploration, but finding that exploration with the right exploration, it seems to be fairly domain specific. And so so that's my frustration with relying purely on data-driven models. And so going back to this slide, to avoid this problem of I'm getting some data and I'm picking a policy that's consistent with my data, but I picked the wrong policy, you need some notion of inductive bias. You need something that tells you what it means to be in that small space of human policies as opposed to arbitrary policies. So you kind of need to answer the question of what makes human behavior not completely arbitrary. And to us, the answer has been that the way people act is a consequence of the decisions they make. The decisions they make is a consequence of the intentions that they have. So they're doing decision making and towards goals, towards intentions. And we have to really account for that when building these models of people. In other words, this is really useful inductive bias to take into account and put into your model. And the question is, how do you do that? So in this world, we sort of look at the scene and say, well, the person's not going to behave arbitrarily. The person has an intent. We don't necessarily know what intent they have, but they might want to go to the door. They might want to go and sit down. They might want to go to the table. Who knows? But it's sort of something like that ends up driving their action. So they're not going to run around in circles like mad. They're going to do something. And so the role of data here, actually, let me just kind of go quickly over this. So they're going to do something, which means that their actions are conditioned not just on the state, but on sort of this thing that they're trying to do, which we're going to call theta. And the way we assume people are driven by their actions, right, is if I have a goal, then actions that are kind of better for achieving that goal are going to be more probable, right, are going to be more likely for me to take. So this is this Boltzmann model that Dorso was talking about. So all well and good. Now where data comes in, so data is still very important here, but the role that data is playing is to identify the space of possible intentions in the first place and to learn a reward function or maybe a Q value function directly that is conditioned on these intentions. And this is not a magic bullet. This doesn't solve everything. If you, for instance, learn directly values, or even if you learn rewards, but they're mapped directly on raw state space, raw kind of input, then you're going to kind of end up with sort of fairly arbitrary models as well. So you have to be careful. It's not sort of a recipe that you just apply and it just magically solves all of your problems. But this is the role that data can play. Now, online, after you've trained your model, of course, you don't know what intent the current person that you're interacting with has. And so what we typically do is we maintain this belief over what they might be doing. So they could be goals, or what Dorsa was talking about, was referring to as sort of like driving styles or their preferences for a task or something like that. And so we don't know what these are, but if I see the person act, right, that's evidence that I get in a Bayesian sense about what their intentions might be. So we can run this Bayesian belief update and sort of adjust our distribution online as we see the person acting. And so now this gives us this way to make predictions forward in time. Again, this is kind of all in simulation, so take this with a grain of salt, but I just want to point out that in our experience, this means that not only can you learn these models, but also you can learn them from off-policy data. So you don't need to close that loop where the robot has to interact with the person using a pretty janky model that is still in the process of learning. You can rely on sort of human-human interaction data and apply it. And it will get you further than black box models if your assumptions are actually anywhere near correct. So if your assumptions are anywhere near correct, then you end up with things like this, where here's a quad order, here's a person, they beautifully navigate around each other. The quad is making predictions about where the person might go, it's making sure it's staying out of the way, everything is beautiful. But as Dorsa was saying, this goes wrong. And one thing you can do that I'll sort of hint at towards the end of the talk is there's all these ways we've been exploring to sort of fix these models and account for various forms of human suboptimality. And I think that's really interesting, and we're still doing a lot of that. What's also interesting is to sort of acknowledge that we'll never get there. We'll never have perfect models. We're never get all of our assumptions right. And so here's an example of this. We spilled some coffee on the floor. You have to pretend with me because we didn't actually want to make our floor dirty, but so we marked it around here with some tape. So that's coffee spilled on the floor. And the robot just does not get to sense that. It just does not have access to the fact that there's coffee spilled on the floor. And so now this is an obstacle that the person is avoiding, but it's an unmodeled obstacle. The robot has no idea what it is. And so unfortunately, with this, no version of systematic bias that you can account for will save you, because you just don't know the actual reason why the person is acting the way that they're doing. So they're being very intent driven, they're being, fairly rational, but they're avoiding this thing that you don't know about. And so you get in trouble. You start making these predictions that say, any moment Silva's gonna turn around and go straight towards her goal. And then, predictors fail, and therefore planners fail, and then you get into these unsafe states. So that's a challenge with, I think in general with data-driven models, it's a challenge when you no longer protect against anything that might happen, is your models can be wrong. And so we asked ourselves, well, what can we do? We'd still like robots to not crash into people, but we can't use the forward reachable set, because that means the car never leaves the garage. So what do we do? And we noticed, well, wouldn't it be nice if, when the person acts in this completely unmodeled way, if we could somehow just use the forward reachable set instead? Because it sure be nice to use the forward reachable set in those situations, because the forward reachable set certainly deals with this problem. It doesn't care about what's modeled unmodeled. It sort of allows for anything to happen and protects against anything. So it'd be nice to kind of fall back on this forward reachable set. The question is how? How do you automatically revert to something like this instead of using it all the time? So, what we want is, along the way, as we see the person, we might, start with these predictions and keep them while they hold, right, with this intent-driven, data-driven model. But then we kind of want the robot to sort of use the forward reachable set when that model no longer seems to make sense. So how do we do this? And the answer is actually kind of interestingly easy when you go back to this intent-driven model. So one thing that I haven't talked about, but that Dorsa alluded to, is this kind of parameter beta that we stick in there. So the model basically is a model for people taking noisy optimal actions in pursuit of their intentions. And the keyword here is noisy, right? We allow for some noise. And so typically we allow for some noise by sort of choosing a value of this beta parameter and saying this, this is about how noisy things are. If we choose a value at one extreme of 0, we're essentially modeling the person as completely arbitrary. So anything goes, any action is just as likely. It's just a uniform distribution, and that's essentially the forward reachable set. So you can see here on the right these predictions and how essentially they just reconstruct the forward reachable set. If we plug in a beta that's high, then we end up with sort of pretty stringent model that sort of insists on the person taking the optimal action. And in between, right, there's kind of this spectrum. We can have 4 reachable sets on the one hand, then sort of relax that a little bit, trust the model some, and then go all the way to no, people are being rational. And so the thought was, well, let's take advantage of the spectrum. And instead of fixing a beta, let's try to see if we can let the data speak for itself and sort of tell us what the right beta is to use at what time. And so the thought was, okay, let's actually not estimate the person's rationality, but actually estimate how rational they appear to us according to the model. And if for any model we have, they appear, if people all of a sudden have sort of low beta, low apparent rationality, if they appear to be not intent-driven, well, then that probably doesn't mean that they're not intent-driven. That probably means that we have no idea what their intent is. That's on us and not on them. And so that's what we're doing. I know I have to wrap up. So that's what we do. Basically, when the person acts, we look at that and say, okay, the person was here, they took this action. let's figure out what our different betas would say about that. So a low beta would assign, some probability to this action. A medium beta would say this action is way less likely. And then a really high beta that insists on the person sort of going towards the door would say this is completely unlikely, right? And so the beta that best explains this is going to be on the lower side. And what we end up, and we do this for all the possible intentions that you have in your space. And if beta is low for all of them, that means that all of them are wrong. That means the person is doing something else that you don't understand. And so then you have this probability distribution that shifts mass. And then the question is, okay, I've detected that something is wrong. The robot has raised the flag. Beta is low. What do I do? How do I become conservative? And there's kind of a hack you can do, which is you switch the for reachable set, but it turns out you don't have to, which is the thing that I really appreciate about this method. And so the moment you've seen the person take that weird action you can't explain, your beta, your estimate of their rationality has become, well, low. And at the next time step, you automatically make higher variance, lower confidence predictions on what they're going to do, and therefore automatically become more conservative, sort of interpolating towards that forward reachable set and taking good actions. Okay, so here's a video of what happens is Sylvia's avoiding that coffee, the uncertainty grows. Here's another example. I might play. Here, the person is going towards a modeled goal and everything works out. Then they're gonna turn and go towards this other model goal and everything works out. And then they're gonna turn around and do something else that we don't know. And the robot's gonna become hella confused. Here it is in a second. Yeah, bam, I don't know what's going on. And just stay there and wait for the situation to clear out and then have a plan. Okay, I'm gonna skip that, I'm gonna skip that, I'm gonna skip that. And I'm just gonna end on, I think humans are intent driven. I think we have to take that into account. Now, the fact that, along with that comes the fact that we're gonna get the notion of how they're intent driven wrong inevitably at some times, and we have to be ready for that. And that's what this line of work was about. This is joined with Andrew Bakshi and Jaime Fisak and a few members of Claire Tomlin's group. Dorsa talked about it, so I don't have to mention it that much, but there's this other thing that's going on, which is when we talk about intent-driven, we shouldn't be talking about intent-driven in isolation. Our models of people have to account for the fact that there are other people and other robots around. In other words, there are other intent-driven agents around. And when you have two intent-driven agents around, you end up with a general sum game. And so you have to adapt your notion of what it means to be rational, what it means to be intent-driven, to the fact that you're actually in this game. And we've, both Dorsa and Jaime and David have all kind of put their own stamp on how to approximate that game when you're in continuous state and action spaces. And then finally, this is kind of what Dorsa was talking about. People have systematic biases. The intent-driven does not have to mean perfectly rational. We can actually evolve these models to understand about more than, okay, the person is just, sticking by this rigid thing. And the approach that we've been taking here is to think of people as maybe not totally irrational, but rational under just different beliefs, different assumptions about the world, about how the world works, what they can see, what they can't see, than what the robot has access to. So admit that there's a disconnect between the robot's notion, the robot's beliefs, the robot's assumptions, and what the person thinks. And so here's a good little lunar lander game. People suck at this. They just crash all the time. If you model them as having a different dynamics model, a different estimate about how the physics of the system, you end up sort of going from trajectories that don't make any sense to actually them being able to take control of the system and sort of safely land it. And there's kind of a line of work that we've been doing in this in terms of identifying all the different ways in which our assumptions could be broken and what people might be assuming instead, and trying to learn that. And this is with Sid Reddy and Lawrence Chan and Dylan and folks from Sergey and Shankar's lab. So with that, I'd like to thank you. And yeah, I think humans are intent driven, and we're still trying to figure out how exactly they're intent driven, but I think that's an important thing to take into account. Thank you very much for listening.
Great, thanks. So I think there is actually a question from Dorsa, right? She is asking, for the lunar lander example, do you think people have different dynamics, or that people just have different heuristics policies to play the game?
Yeah, that's a good question, Dorsa. So of course, in a sense, we don't know because we can't probe into their hen. But what we found is that when we end up estimating the internal dynamics model that they might be assuming based on their actions. So say, can their actions be explained by being rational plus assuming a different dynamics model? Of course, that better explains that their actions is not surprising because we just added extra degrees of freedom into the model. But what's interesting is that this then actually helps us better infer their intent and better assist them. And so there's kind of two different ways that we've validated, in a sense, that doing this is helpful, which at least suggests to me that there's some notion of, I don't think it perfectly explains what's going on, but I think it's a piece of this puzzle, right? That maybe it's not all heuristics and hacks, because you can do like a fairly principled thing and it ends up actually accounting for a lot of what appears to be heuristics and hacks. And I guess that, I thank you for that question. I think that's kind of been the realization for me, that we can try to do heuristics and hacks. And I think, behavioral economics has a ton of different heuristics that we can try to sort of account for in various ways. But I would prefer to sort of try the principled thing and see how much of that it can explain. And I'm sure it won't be able to explain everything, right? But I think what it can explain will actually end up being a little bit more generalizable. So, so I think the truth is somewhere in the middle.
Great, thanks. I think we should move on. Thanks again for your talk. And maybe if there are additional questions, you can maybe answer them in the chat. Thanks.
Okay, thank you.
Yes.